I would like to review what we did last time, which is the first thing is we tried to generate an equation for the oil recovery versus time. And we had this equation that we had to solve, but it involved an integral. The integral was a little tricky, so what we did is integration by parts. So we walked through those steps, and we remember that the integral of x dy is the integral of dxy minus the integral of y dx. In our case, x is the fractional flow of oil, and dy is dtd, the dimensionless time. So we did that integral, and you have this integral from over here, and this integral is super simple, so it's just FOTD. And then this integral is TD times DFO. And that one's still not quite clear how we do that, but we remember that at the production well, or actually always, TD is, or at the production well, TD is 1 over the derivative of the fractional flow curve. So TD is 1 over dFW dsW. And since FO plus FW is 1, that means that DFO is minus DFW. So you have a negative here and a negative here. Those cancel and you get a positive. Also, this DFW here cancels with this DFW. And so then the DSW flips up on the numerator. So now you have the integral from 1 DSW. Integral of 1 is super simple. And so the limits of integration there, SWI to SWP. So here is the solution for the oil recovery versus time. So NPD, well, let me do one more thing. So we need to remember that FOP, that's the fractional flow of oil at the production well, is 1 minus the fractional flow of water at the production well. Also, the dimensionless time is again 1 over the derivative of fractional flow of water. So I can write my equation here as NPD is equal to 1 minus the fractional flow of water at the producer well divided by the derivative, F prime, of water at the production well plus the saturation of water at the production well minus the initial saturation. Or another way to write it is the average water saturation minus the initial water saturation. This gives what we call the Welge equation, which says that SW bar is equal to the water saturation at the producer well plus 1 minus FWP divided by F prime WP. Again, SW bar is the average saturation throughout your reservoir. Okay, so what are the steps to get NPTD? And of course, this is something that you would be very interested in as a reservoir engineer, right? You would want to make predictions about what your oil recovery would be with time. I mean, that would be fantastic if you could tell your boss, you could tell your company that, look, if we're doing what we're doing, this is how much oil we're going to be recovering in 2 years from now or 10 years from now. And that helps you to make some decisions about doing some different things. So the first time is that you're going to make this plot at different times. So you choose a dimensionless time. And at the producer, XD is equal to 1, right? Because XD is equal to 0 is the injector, XD is equal to 1 is the producer, and then XD is something in between the injector and the producer. And by definition, that's the dimensionless time times the fractional flow, derivative of a fractional flow of water at the producer well. So that means that the derivative is 1 over TD. So you chose a TD, you invert it, and that gives you the derivative at the producer well. Well, now that you've got the derivative and you have a plot, remember you did this on your homework, of F prime versus water saturation. At that F prime, you can come across and find the water saturation. So you use the derivative of the fractional flow curve to determine SWP. So if this was 1, you'd come over here and you go down and you would get something between 0.3 and 0.4. Now that you have SW at the producer well from this curve, you go up to the top curve, which is the original fractional flow versus water saturation curve, and at that same saturation you come up, go across, and you find FWP. Now that you have FW prime of P, SWP, and FWP, you can calculate the average water saturation, and you could subtract it off from the initial water saturation. That gives you NPD. Now remember, at early times, before breakthrough, the dimensionless recovery, NPD, is equal to the dimensionless time, TD. And that's why we had a plot that looked like this. So at early times, NPD versus TD is a nice straight line. And then at later times, once breakthrough happens, then we're producing both water that we injected as well as oil, and the oil recovery tapers off quite a bit. So what you're doing is you're producing a lot of water and it's not all oil. So early on, you might be injecting 1,000 barrels of water and you're producing 1,000 barrels of oil. That's great. But then all of a sudden, after breakthrough, maybe you're still injecting 1,000 barrels of water, but maybe of the 1,000 barrels you're producing, 700 of them are water and only 300 are oil. And then it gets worse. Then it's 800 of water and 200 of oil, and etc. Okay, so we did that last time. And then we said that we have to consider something, which is the real fractional flow curves and derivatives look something like this. And one thing that's tricky is that this derivative goes through a maximum. So it's 0 at the residual water saturation, it's 0 at the 1 minus the residual oil saturation, and then it reaches its peak. And what that means is that at a given derivative, there's actually 2 points on this curve. But we're not going to use both points. And it actually causes a problem. Remember that the velocity of a saturation front, VW, is equal to dFW dsW. And so if you follow the procedure that we described in the previous 2 lectures for calculating the saturation of water along the reservoir from the injector all the way to the producer, so SW versus distance, if you follow that procedure for a normal relative permeability curve, you'll get something funny, which is you start at 1 minus SOR, it's decreasing, which makes sense, but then it gets to this point and it comes all the way back. And then of course you have an initial water saturation and you have this over here. So at the same distance you've got these 3 saturations. And that doesn't make much sense. Okay, you can't have more than 1 saturation at a particular location. So this is mathematically what we get, but physically that's not what we get. What actually happens is that some distance, I'm going to call it XDF. XD is of course the dimensionless distance. The F subscript stands for front. So we have this shock front, and at that dimensionless distance XDF, there's a water saturation SWF, which is the front saturation. And the true curve comes down and comes to this point and then drops quickly, immediately in theory, all the way down to the initial water saturation, and it's equal to the initial water saturation everywhere past the front. Remember that this is just a snapshot in time, and if you were to do different times, you would get different plots. And we need to understand this so we can create our oil recovery versus time plot. One thing that I said last time is that this shock front, you can almost think of it as a wall, as a moving wall with time. And that moving wall is pushing the oil all the way towards the producer as you go along. And if it were a perfect wall, it would just push it out like a piston. Once the wall got to the producer, you would have produced all the oil you can, and then you would be done. Unfortunately, that's not how things work. They're not perfect. Instead, I would describe this shock front as a leaky wall, a wall that pushes the oil, but it doesn't push all the oil. Some of it gets left behind. So all this oil over here, okay, is oil that's left behind. We call it unswept or bypassed oil. Now, if you keep on injecting water, even after breakthrough, you will produce that oil, just slowly. Okay. All right, so I'm going to shift gears now a little bit. We needed for our oil recovery plot and for this plot over here, we need to know what SWF is, the water saturation at the front. So we need a way to calculate that. And so that's what I'm going to do now. So I'm going to go to the .cam and our goal, so the goal is to determine SWF, the water saturation at the shock front. Okay. All right, so what we're going to do is we're going to go back to our material balance because we always know that mass is conserved. And the mass of water is conserved, the mass of oil is conserved, the overall mass is conserved. And remember, if we had a 1D reservoir or a 1D rock core, and maybe we were injecting water here, maybe we're producing oil, okay, plus maybe water. And we did a mass balance at a particular location. Let's do the mass balance at a location, XD is equal to XDF. XDF is the front position. And we know that SW at this location changes very quickly from SWF to SWI. It changes quickly, and I use the word quickly, I mean it changes over an infinitesimal distance, right? I'll go back to this here. We saw that XD, that SW goes from here all the way down to there immediately, right, over an infinitesimal distance. It also, since this is a moving front, since this is a time-dependent problem, even if it's equal to SWF at one time, a second or a nanosecond later might all of a sudden equal to SWI. Or I should say vice versa. It would have been SWI and then it's equal to SWF. So we can write a mass balance here at that position. And we did the mass balance earlier, but I'll revisit that. So we know that in minus out is equal to accumulation. And this is a water balance. We'll just do it on water. Okay. So the mass in to this control volume is the density of water. That's a mass per unit mass per volume times the rate of water, QW, which is a volume per time, times a delta T. And that's at a position, we'll say X, or I could say minus rho W, QW, delta T at X plus delta X. Okay, so this is X and this is X plus delta X. Or I could say XDF and XDF plus delta X. So this is what goes in, this is what goes out. And then there's some accumulation of water, right? So the amount of water in there might change with time. And then that looks like the density of water times the pore volume, which is A phi delta X. That's at T plus delta T minus rho W A phi delta X at T. So A delta X is the volume, right? A times the distance times the porosity is a pore volume, so that's volume times the density, is mass per unit volume. That gives us the mass. So this is the mass at time t, and this is the mass at some future time t plus delta t. If we're again assuming that we have incompressible fluid, so my densities change, and then I can recall QW is Q times FW. Q is the total rate, FW is the fractional flow of water. Okay, so recall that the water rate is the total rate times the fractional flow. And so what I can do is I can write this as QW is Q times the fractional flow of water at the front minus the fractional flow of water injected, right? Because right here maybe we have FWF, and a very small place downstream you might have FWI, and that's over a time delta T. On the right, what we can do is we can say A phi, A times the porosity, times the water saturation at the front minus the initial water saturation times delta X. Why is that? Because the water saturation could be SWI at time t, and at a short time later, all of a sudden it's equal to SWF. So we can write that. We can rearrange this equation. So I can rearrange and say that delta X over delta T is equal to, well, Q over A is the Darcy velocity U divided by the porosity phi times FWF minus FWI by SWF minus SWI. Okay. Let me talk about that just for a minute. So U is, of course, the Darcy velocity. It's the production rate Q divided by the cross-sectional area A. Phi is the porosity. FWF is the fractional flow of water at the front. FWI is the initial water saturation, the fractional flow of the initial water saturation. And if that's residual water or irreducible water saturation, then that will be 0. And for the purposes of this derivation, I'll probably assume that that's the case. SWF is the water saturation at the front. Remember, that's what we want to solve for. SWI is the initial water saturation, which may be equal to the irreducible water saturation. If I put this in dimensionless units, delta XD over delta TD, then I can write this as FWF. Oh, and if this is irreducible, then I can say that that's 0. And this is SWF minus SWR. And I've got this equation. Then I'll say also, we know that the velocity of the saturation front, VW, is equal to partial of XD with respect to TD, which is equal to partial of FW with respect to SW at the front saturation. We derived this a couple lectures ago. If I compare these two equations, and I look at, these look very similar. This is a partial derivative of XD with respect to TD. This is a change in XD over delta TD, but in the limit that delta TD is really small, this is equal to this. And so what that means is that FWF over SWF minus SWR is equal to FW prime at SWF. Or So the fractional flow of water at the front is equal to the water saturation at the front minus the residual saturation. This is presuming that our initial saturation is SWR, times the derivative of the water fractional flow at the waterfront saturation. We have a curve of fractional flow FW versus water saturation SW that looks something like this. All right, this is one, at least in the absence of gravity. This is 1 minus SOR, that's SWR. And we have that curve. And what we also want is some location on here, SWF, that corresponds to an FWF. And what we have is an equation here that looks like a line. It's like y is equal to a slope times x minus x naught. So this is like an x-intercept. So it's a line. And I can draw that line that as an x-intercept of SWR, starts right there. And the trick is that it has to, I'm going to draw a line, but it's got to touch the fractional flow curve somewhere. It's like a tangent to the line. We call it a breakthrough tangent. And if you draw the line in such a way that it just has a tangent to there, then the one place where it touches is the water saturation, and this is FWF. So this line is kind of like FW is equal to SW minus SWR times the slope, which is FWF prime. Okay, but the key point is that if you draw this line from your initial saturation, in this case our irreducible water saturation, and you draw the line such that it is a tangent, it's got one point where it touches the fractional flow curve, that point is the front water saturation, which is what we wanted, and also the front fractional flow of water. So now we have a procedure for calculating SWF, and then we can do everything else with that. I showed you last time that a typical plot of water saturation versus distance looks like this. At a given time, it comes down, it decreases, has a shock front, and then goes down. At a later time, it decreases more slowly, and then it has a shock front, and the saturation at the shock front is SWF. And what we said is that in order to make this plot of SW versus XT, we need to know what the saturation at the waterfront at the front is. We have a plot of fractional flow versus water saturation. And on Friday, we're going to do an example problem together. So look for your email, look on Canvas. I'm going to post some things for you, and we're going to do some things with these plots. You'll have to, bring make sure you have a pencil, make sure you have some sort of sharp edge like a ruler or something so that you can draw these more quickly. But we'll spend maybe the majority of Friday doing an example problem together. And so what you want to do is you want to draw this tangent which goes from the initial water saturation and you got to find that place where it just barely touches your fractional flow curve. It looks like this, and this point is going to give you SWF and FWF. So now you have SWF. And from that you can make all your plots, including maybe the most practical plot, which is, oh, I can't find the paper now. Oh well, maybe I left it, but it's going to be the oil recovery versus time plot, all right? And so we learned of a procedure for do that. That procedure well, I'm gonna go through these slides again because I think this is complicated and we want to do that. So, okay. As a reminder, water saturation versus distance looks like this. We're trying to find that position, XDF, where SW is equal to SWF, and we have that shock at a given time. To find SWF, we did a material balance on water. We chose a position, XDF. We don't know what that position is yet, but there's some position, XDF, where you have the shock. And at that position, what happens is that the water saturation changes abruptly from SWF to SWI. So if I do my mass balance, the mass of water into that control volume, that little sliver between those two lines, is given as the density times the water rate times delta time. That's what goes in, and then what goes out is the same thing, but it's at a different position. And the water rate is going to be different at x and x plus delta x. Because there's a difference, that means that some water accumulates or deaccumulates in that control volume, and that's given as the pore volume, A phi delta x, times the water saturation, that's the volume of water, times the density of water is the mass of water. And the water saturation at T plus delta T and at T are different. So at T, it could be equal to SWI, the initial water saturation, but at a slightly longer time, all of a sudden it changes to SWF. And so if I cancel my densities there, and I recall that the QW, the water rate, is equal to total rate times the fractional flow of water, my mass balance reduces to this. FWF is the fractional flow of water at the front minus the initial water saturation. SWF is the water saturation at the front minus SWI. I rearrange and I get this equation over here. Okay, and I've assumed that SWI is equal to SWR, which is why the fractional flow of water is 0 at that place. So I'm going to use this, and I'm also going to use what we had learned before, which is the velocity of the saturation front is given as the derivative of water with respect to saturation at SD, and we're interested in SWF, that particular saturation. Remember what I told you the last two class periods is that, remember those blue dots? I said we could choose any saturation and we could follow how fast they move along the core. You can choose any saturation. I'm interested in the front saturation. That's why I'm going to do it at SWF. And these two equations look similar. This is a discrete derivative. This is a derivative here. You could set them equal to each other. And when you do that, you get an equation that looks like this, which is effectively a line. Basically says the fractional flow of water is equal to a slope times, put it, water saturation minus the initial water saturation. And what you get is these breakthrough tangents. So as I showed just a moment ago, this is what you do, is that you draw this breakthrough tangent from your initial saturation all the way to the top, and it should touch at one place. If you go down, this is SWF, which in this case is about 0.7. And if you go over, then this is the waterfront fractional flow, which is 0.91. Now that's interesting, because what does that tell me right there? That the fractional flow of water at the front is 0.91. That means that before the front reaches the producer well, I'm producing 100% oil. So FW is 0 and FO is 1. As soon as that front touches the producer well, all of a sudden I'm producing 91% water and 9% oil. That is discouraging, right? So if you were a reservoir engineer, especially decades ago before you understood this math, and you were producing all this oil, and then all of a sudden you just started producing 91% water, you'd be disappointed. That doesn't mean that it's economical. Maybe that 9% oil is still going to make you money, but it's not ideal, but that's what happens. And so this is the fractional flow there. And then if you wanted to find the derivative, then you also choose 0.7. You come across and you get the fractional flow of derivative of fractional flow of water, which is 1.81. And we know that if we wanted to make an oil recovery plot, then we'll need to know these variables. Okay, so to recap, the water saturation is on the y-axis. The dimensionless distance is on the x-axis. And what we have on the right is what our mathematical solution was. We get this thing that does this, and it comes around, and then it does this, and that doesn't make any physical sense. But there's some location, XDF, where you have the shock front. And so with the physical solution, looks like this. This is our wall. This is our leaky wall that's moving from left to right at different times. Remember, this is just a snapshot at a time. And one of the things that you'll need to do is to make this plot. So to make this plot, what you do is you determine XDF and SWF using the method we just did a moment ago, which is this breakthrough tangent. And if this water saturation is less than SWF, then we use the equation we derived a couple times ago, which is the position XD, so this position over here, is equal to the derivative of the fractional flow curve at the water saturation. Remember, we're only choosing water saturation is greater than SWF, and you multiply by the dimensionless time. So what you're doing is you're plotting points from here all the way to SWF or XDF. And then for any water saturation, for any position greater than XDF, SW is just equal to SWI. Okay, so one of the things that I'll probably ask you to do in a homework, I might ask you to do in an exam, is to make this type plot. And we're going to do an example on Friday, which I think it'll make it more clear. So to summarize, the steps for generating the saturation profile at a given time TD is first off, you got to choose a time to make the plot. So maybe I give that to you on a test, or maybe you choose something you would want to do. So you choose that TD, and remember that TD is the dimensionless pore volume. So Q times T is the volume you've injected, right? It's a rate times the time, so it's the total volume injected. And the denominator is the pore volume. It's the bulk volume, AL, times the porosity, which gives you the pore volume. So that's a dimensionless time. Then you create your fractional flow, FW versus FW, using your relative permeability curves. you did this on your last homework. And in the absence of capillary pressure or gravity, it's super simple. It looks like that. If you have capillary pressure or gravity, it is going to be more complicated. At a given water saturation, for example, you might start at 1 minus SOR, you compute FW prime numerically. In other words, so you have that plot of FW prime versus SW, which is and again you did that on your last homework, and from the saturation of interest you calculate FW prime. Then you compute XD, the position, at that water saturation in TD. Remember, the formula looks like this. So I chose a TD, that was step 1. I calculated the derivative at a particular saturation, that was step 3. I multiplied the two together and I get my position. So now I plot my point. I chose a saturation, I calculated an XD, and I plot that point. And I repeat that process for a bunch of different points. Repeat that for all water saturations. But you want to be careful. You want to be careful because you only want to do that up to SWF. So I said repeat for all SW from SWR is less than SW to 1 minus SOR. But really, I should have said up until SWF, the front water saturation, and at saturations above that point, then we know that then the water saturation just becomes SWI for any XD greater than XDF. Let me also discuss again how we do the oil recovery plots. So the steps for that are we calculate SWF again from a breakthrough tangent on the fractional flow curve. We use the derivative of the fractional flow curve to compute the breakthrough time. This is not new. This is something we learned already. So the breakthrough time is 1 divided by FW prime at that front saturation. But I guess the difference is that now we know how to calculate the waterfront saturation, which means we know how to calculate the derivative at that saturation. Prior to breakthrough, we know that the fractional flow of oil is 100%, or the fractional flow of water is 0%. And the cumulative recovery is the time, is just TD, because we're producing 100% oil. After breakthrough, we have this equation. Remember, that was the Welge equation that we developed. And then you can plot NPD versus TD, which is what we had before. So going back to the water saturation versus distance curve, this is water saturation versus distance at different times. So I've chosen a dimensionless time of 0.1, a time of 0.33, a time of 0.55. Notice that the SWF is constant at all times. There was a good question last time, which is why is it constant at all times? That came from a material balance. And what we learned is that SWF comes from that breakthrough tangent, and that's true regardless of the time. I chose 0.55 for a very specific reason. It is equal to 1 over FWF prime. That is the breakthrough time. So the breakthrough time is 0.55. The breakthrough time is always, always, always less than 1. Okay? It would only be equal to 1 if it was a perfect piston and it was pushing all the water, all the oil out, and then the water didn't reach the producer well until 1 pore volume. But that's not what happens in real life. It bypasses the oil and it reaches the producer well too soon. The later the better. If TD breakthrough was 0.9, you would be ecstatic. If it's 0.05, then that's kind of disappointing. What determines that breakthrough time? Well, clearly the fractional flow curves Fractional flow curves are dependent upon things like relative permeability and viscosity. You might be able to control your viscosity of your fluids, like your water. That's what we do in enhanced oil recovery. We add polymer to make it more viscous. Or you might be able to do some things to improve the relative permeability. But again, those are sophisticated techniques and enhanced oil recovery techniques. And so the question is that could there be 2 points where this intersects? Not really. Now, one place it does intersect is here at the residual water saturation. That's the starting point. But that one doesn't count. And so if you fix this so that FW is equal to SWR, and then you draw this line, you draw it in such a way that it only intersects 1 point. And because of the shape of the curve, it will only do it 1 point. So, you know, there are curves that you could draw where it would, you know, intersect more than once if it did something funny like this and crossed it, but that's not what these fractional flow curves look like. So when you draw it in such a way that it only touches 1 point.